Okay, next I will calculate the electric field. So we will assume that there is a charge on the plate. So next we will calculate the electric field between the plates by using Gauss's law. So here we have calculating the electric field. We know that electric field is related to the charge by using Gauss law is E dot dA is equal to the flux through any closed surface. This is the closed surface is equal to the charge enclosed by the closed surface over epsilon naught. This is the Gauss law. Now here I will consider two parallel plates of a capacitor. Suppose we have this plate, and this plate we have positive charges, and we have another plate which is this one, and this one we have negative charges. Now I will draw a Gaussian surface. This is the Gaussian surface. This is Gaussian surface. Now here the electric field direction is from positive to negative plate. So the electric field direction is this one. Now if we look at here in this equation, we have the area element dA. We can take only those area element through which the flux passes. If we look at here, the flux passes only through this area. So I will consider a small area element here. This is the small element area dA. Its direction is this one. The area direction is this one. I call it n unit vector, and this is electric field direction. So if you look at here, the electric field direction and the area direction, they are the same. They are parallel to each other. So it means that the dot product will vanishes here, and we have this relation which is E dA is equal to Q over epsilon naught. Now on this surface, this Gaussian surface, the electric field is constant everywhere because it is an equipotential surface. Like the distance from this part of this plate is to this Gaussian surface is same as this one to this one, or as this one to this one, or as this one to this one, or as this one to this one. So the electric field is constant throughout this surface. If it is constant, then we can move it outside of the integral. So we have E into dA, which is equal to Q over epsilon naught. Now E integral of dA will give us the total area, but this is the area of the surface through which electric field lines passes or the flux crosses. This is this area, not the whole area. It is only this area because the electric field line only passes through this area. If I consider this area, then there is no electric flux, so the flux through this area is 0, the flux through this area is also 0, the flux through this area is also 0. So we have left only this area. So this is the area of this surface through which the electric field line passes is equal to Q over epsilon naught, or we can say that E is equal to Q over epsilon naught times A. This is how we calculate the electric field. Next we will move to calculating the potential difference. Now one thing more, the Gaussian surface, here the Gaussian surface is drawn in such a way that it enclosed the charge on the plate. So it enclosed the charge on the plate. And we take area A of that part of the Gaussian surface through which flux passes. So this is the idea behind calculating the electric field. Next we have to move towards the calculation of potential difference, like calculating the potential difference. The potential difference. Suppose we have these two plates, then the potential difference between the plate is related to the electric field through this relation. We know that VB minus VA, which is equal to minus A to B E dot ds. Now here the path of the integral, we will define the path of the integral. The integral is evaluated along any path starting from one plate to another plate. Like the integral can be evaluated from here to here or from here to here. But for convenience or for simplicity, we consider the path from positive plate to negative plate, or we can consider the path of the integral as the direction of electric field. Here the direction of electric field is from positive charge to negative charge, so the path of the integral will be from positive plate to negative plate. Now for this path, if I consider this path from positive to negative, then we know that electric field E and the area element ds, they are both parallel. If they are both parallel, then this part will be positive, so this quantity, it will be negative, because this is positive, so we have a negative sign here, so it means that this quantity is negative. We can say that the quantity VB minus VA is always less than 0. For which path? For the path of the integral starting from positive plate to negative plate. Because the direction of electric field E and the direction of area ds or area dA, they are both parallel. If they are both parallel, then this quantity will give us a positive number. If this is positive, then we have a negative sign, so as a whole this quantity is negative. This quantity negative means this quantity is negative. So VB minus VA is always less than 0. For which path? If we move from positive to negative. But we are looking for absolute value of potential. Absolute means the positive value of potential. So we can say that we replace this term VB minus VA by a negative term minus V. This represents the total potential up here across the plate. This is the difference and this is the total potential. If I put this in above equation, then we have V minus V is equal to minus integral from A to B E dot ds. So minus cancel with minus, so V will be equal to integral of E dot ds. But the path of integral is from positive plate to negative plate. So I replace A to B by positive to negative. So this positive and negative sign here on this integral remind us that the path of the integral is from positive plate of the capacitor to the negative plate, like it's from here to here. This is the path of the integral. So this is how we can calculate the potential after calculating the electric field. Now I will apply all these steps to an actual problem. So here I will calculate the capacitance of a parallel plate capacitor. Capacitance of a parallel plate capacitor. So I think the length of this video is too much, so I will start in the next video. Thank you.